In week 1, when we were first talking about limits, we had an example about the height of a ball. In that example, we were worried about what the speed of the ball was at some certain point. Let's return to a related example now that we know something about derivatives. Suppose that we have a particle traveling along the path s of t equals negative 1/2 t squared plus 7, and we're interested in t equals 0 seconds until t equals 3 seconds. The question that we want to ask is, how fast is a particle traveling at t equals 1 second? So our first idea is to look at a graph of this function near the value 1. So if we sketch the graph and zoom in a whole lot, the function looks approximately like this. Here's x equals 1. Here's the function, doing something kind of like this. So I am curious at how fast the particle is traveling at t equals 1 second, so I'm going to test out some points that are near t equals 1. What if I try here at 0.5 and here at 1.5? Well, we can figure out what the function values are. Here at t equals 0.5, the function is approximately 6.875 meters. And at 1.5, the function is approximately 5.875 meters. So the slope of the line segment in between these 2 points is approximately the slope of the tangent line to the curve at 1. It's not exactly the tangent line to the curve at 1 because I have moved off of the function a little bit. So if I ask the question, what is the slope of this tangent line? I can figure it out using the slope formula. So the slope of the orange line is 6.875 minus 5.875 all over 0.5 minus 1.5. And so if we simplify that, we see that the slope is negative 1. What if I try some points a little bit closer? Well, maybe I'll move halfway in again. What if I ask, what is the function value at 0.75? Well, here I come up and I find that the value at 0.75 is approximately 6.7188. And what about halfway between here at about 1.25? Well, at 1.25, the function value is approximately 6.2188. So again, I could ask, what is the slope of this little green segment? And I can calculate it using the slope formula. I get 6.7188 minus 6.2188 all over 0.75 minus 1.25. And again, I get approximately negative 1. Approximately because these function values are approximate. So what we're doing in this case is looking at 2 different function values and sort of shrinking them towards the function and saying, how can I use these secant lines to approximate the tangent to the function at the point 1? The tangent is here, approximately, and the function value at 1, we'll need this in a minute, is actually 6.5. All right, so we're starting to look at what's happening with this limiting process, and we'll see that this actually tells us a lot about the derivative. We know that the derivative is the slope of this tangent line, and so we can find it by taking the limit of the slopes of these secant lines as we get closer and closer to 1. So from this, we have a little bit of evidence that the slope of the tangent line should be negative 1, but we'll need a little bit more information in order to figure that out. Calculating the slope of some secant lines to the graph has given us an indication that we think that the slope of the graph at t equals 1 should be negative 1, or that the ball is moving about 1 meter per second at that time. But these are only indications, and we've only seen a couple of secant lines. What we really want to do is actually take a limit in this case so that we can figure out the actual instantaneous speed of the ball and the actual limit of these secant lines that we're creating. here we again have our position function, and let's use the definition of the derivative to figure out what the slope of the tangent line should be. We'll use the other definition, the one that we have been using a little less frequently. We know that by definition, s prime of t is equal to the limit as t approaches the value that we're interested in, 1, of f of t minus f of 1 all over t minus 1. The reason that I want to use this definition is that this tells me a little bit more about what's happening with the secant lines, except instead of the 1.25 or 1.5, I'm actually picking the value at 1. So if I come back and look at what's happening with the graph, these would be like secant lines that start at some point here and end at 1. And I'm just moving the function closer and closer along this side to 1, or start over here and end at 1, and I move closer and closer and closer to 1. So you can see that as I shorten the secant line, it should get closer and closer to the tangent line here. So let's evaluate this limit. Limit as t goes to 1, f of t minus f of 1 all over t minus 1. Ooh, this should be s. S of t, s of 1. Very important to make sure you remember what the name of your function is. So here we have the limit as t approaches 1. S of t is negative 1/2 t squared plus 7. And we said we already know that s of 1 is equal to 6.5. And on the bottom here, we have t minus 1. So now, I calculate the limit by taking off the parentheses. I don't really need them. And then 7 minus 6.5 is just 1/2. So this is the limit as t approaches 1, negative 1/2 t squared plus 1/2 all over t minus 1. Since I have 1/2 in this term and 1/2 in this term, let's go ahead and factor that out. So limit as t approaches 1, we'll even factor out negative 1/2, so we get positive t squared minus 1 all over t minus 1. And now, those of you who are great at factoring are really recognizing that this t squared minus 1 is something that we'd like to factor. So let's go ahead and do that. So this is the limit as t approaches 1 of negative 1/2, that t squared minus 1 factors as t plus 1 and t minus 1, and this is all over t minus 1. Well, here's a t minus 1 in the numerator, here's a t minus 1 in the denominator, so we can go ahead and cancel those. Now, I have the limit as t approaches 1 of negative 1/2 t plus 1. I don't have a denominator anymore, and in fact, this is just a polynomial, so I can go ahead and plug in t equals 1. So I get negative 1/2 times 1 plus 1, which is negative 1/2 times 2, or negative 1. So the slope of the tangent line is in fact negative 1, just like we guessed. Now we know without a doubt that the slope of the tangent line at t equals 1 is negative 1, or that the ball is moving 1 meter per second downward at the time t equals 1 second. This is really great. We've seen the connection between what we did with the height of the ball in week 1 and this limit process and the derivative of the function. If we actually calculate the derivative of the function at t equals 1, we find that the value of the derivative really is negative 1. So that example we did in week 1 actually set us up really nicely to understand what derivatives are and why we care about these kinds of limits. Make sure you're keeping up with your practice problems, working on the quiz for this week, and posting your questions on the forum.